Hello, everybody. So we are back again. So we are going to discuss logistic mapping in this class, and the theory of logistic mapping and all we have discussed already during your classical mechanics paper, that is non-linear dynamics. And we are going to discuss the program, how you are going to simulate the bifurcation diagram using Python program. So our question is, plot the set of fixed points x against the control parameter k for the logistic map function xn plus 1 is equal to k xn into 1 minus xn, for the value of k lies between 1 and 4 and xn is 0 and 1. And we'll just have a brush up of our knowledge that we have discussed, or in the classes, classical mechanics classes or the nonlinear dynamics classes we have already discussed. And this equation is a nonlinear equation. So the thing that we have to know about a nonlinear equation is that we know it leads to, that is, this type of nonlinear equations gives some results that is completely unpredictable. It leads to some chaotic situations. Okay, linear equations we can solve it easily. If there are some square terms, xn into xn means there is x square, then the equation becomes nonlinear. And this specific type of nonlinear equation lead to a chaotic situation for certain values of control parameter. K is called the control parameter, and the value of k is restricted to 1 to 4. And these things we have already discussed. You just go through your classical mechanics notebook. It will be well written there, so no need of explaining further how you're getting the value of k and all by drawing the phase space diagrams and all. And the xn, it was actually the did by, and this equation was obtained by Worldhurst, who studied the population of insects in a field. And xn is what? Xn is the ratio of present population to the maximum population. So it cannot have a value which is greater than 1. So xn have a range of values starting from 0 and up to 1, and k control parameter from 1 to 4. And we are plotting the graph between fixed points x, and these fixed points are called attractors. Okay, we'll give some initial values of x, that let it be 0.1, and you find the new value of xn, let xn be 0.1, and you find the new value of xn plus 1. So you'll get some new values, and this process will be repeated for a long time unless and until you get a set of constant values for xn plus 1, and this xn plus 1 becomes the fixed point, and this fixed point is called a attractor. Okay, so we are plotting the graph between all these attractors and control parameter starting from 1 to 4. And the thing is that this yields us the bifurcation diagram. At certain values for k, what happens? The attractors become 2. Okay, that is there occurs a bifurcation. Two attractors will be developed at certain points. At certain values of k, what happens? The number of attractors become 4. Okay, so when the value of control parameter reaches above 3.5, what happens? That we get a lot of attractors which do not have any connections. That then the nature of the attractors becomes strange. Such attractors are called strange attractors. Okay, so if you go, if you just watch here, you can see. Okay, this is the bifurcation diagram. That is actually the graph is drawn between the fixed point of the population and the control parameter, and the control parameter moving from 1 to 3, you get, after continuous iteration, you get single value for the attractors, and it reaches beyond 3 or 3, what happens? There will be 2 attractors, splitting occurs. Then at 3.5 it becomes 4, then at this point it becomes 8, and beyond 3.53 and all, there will be a lot of attractors, and it becomes it shows a strange behavior, and this region leads to the chaotic situation of that equation. So hope it is clear. This is what we're going to plot in this class. So you can go through the theory regarding it. That is, we are having the equation xn plus 1 is equal to c, or we'll change it as kxn into 1 minus xn is our equation. Okay, the value of k is between 1 to 4, and our equation, our mapping equation is fx is equal to ck into 1 minus x. And what happens here is that you go through that one and you can see at a particular point, that is when attractor is reached, xn plus 1 is equal to xn star, and already xn also will be equal to xn star. So both xn plus 1 and xn becomes xn star. It reaches a constant value, that is a single attractor. And on substituting, what you will get the value for the attractor for a given value of control parameter, that is 1 minus 1 by c. And this is possible only in the case where that number of attractor is 1, that is up to 3. Then the situation changes. This things and all is possible up to 3. And when c is equal to 3, the attractor bifurcates to 2 points, and if c is further increased for 3.5699, an infinite number of bifurcation occurs. And what happens? And the attractor becomes strange, and such an attractor is called strange attractor. Okay. Now we have to plot what? We have to plot the graph, or we have to obtain the bifurcation diagram. For that we need an program. Before doing the program, we need algorithm, which is a step-by-step approach for tackling a problem. And the algorithm, the first step is start. Then you will have to define the function, and our function is what? F of cx. Or let it be, I have named it as k, and I can write f of kx. Define the function f of kx. Return the function values means we'll have to return what? Return the function value, comma. It is k into x into 1 minus x is our function value. Input ki, initial value for k and final value for a, which is the control parameter ki and kf. And what? We have to initialize two lists for the value for k's and values for x. We have to plot what? We have to plot the value for control parameter k and the fixed point attractors x. So we'll have to initialize a list. For plotting means we need a set of values for k and set of values for x, which are the attractors. Okay, so what is needed? We need a list. Then what is needed? That see her k changes from ki to kf. Ki or kf is already given here. K changes from ki to kf. Then we'll initially take the value of x to be 0.1, and I varies from 0 to 999 loop, and this is what we are calling x is equal to f of kx. Means what? I'm calling a function, this function f of kx is my initial function. This is f of kx is my initial function, and when we are calling the function f of kx, it returns what? Kx into 1 minus x. So that will be discussed in the portion functions and modules. Okay, how we are calling the functions and all. And for k is equal to ki to kf, we'll have a value for x, that is 0.1, and we'll do the iteration 999 times, so that within the loop, so that we'll reach the value for the attractor. And we'll again do this. Once the value of attractor is reached, what happens? At certain cases there will be a single value of x, and certain cases there will be two values of x. At certain points for control parameter there will be 4 values, 8 values, and beyond 3.53 there will be infinite values for the x. So for getting all those values, we'll do the iteration again. This first loop is for getting the attractor. Once we reaches the attractor, some attractors show gives 2, 4, 8 and infinite values. For getting that, you'll do this one. You'll go to another loop which run again 999 times, so that we can append all these values for control parameter and x to the corresponding list. Then you can plot f of okay, we have named it as k, so I'm changing append k to append k to lk and x to lx. Then we plot lk versus lx, then stop. So these are the steps that we have to follow while writing the program. Next is writing the program. In the program, instead of k everywhere we have used c for control parameter. I'm not going to edit it. Okay, you can hope you can understand that instead of k we have used c. Okay, logistic mapping program, and from pylab import star means all the plotting functions are defined in this pylab module. So if you are not using means you will not get the plotting functions. Now we will define f of cx, that is function definition, and return cx into 1 minus x. Then you will have to give initial and final value for the control parameter, that is ci and cf, that is input range of control parameters. Then I have initialized a list lc and lx for plotting or for getting all the values into this list. Then for c in linspace, ci cf 1000, that is c varies from what 1 to 4 for 1000 values. We are creating an array. Okay, and x is equal to 0.1 for I in range 1000. This first loop is for obtaining the attractors, and second loop is for getting all the values for the attractors. And we'll append c values to lc and x values to lx, then plot lc lx with dot. For getting dot, I need to put dot within the quotes. Then x label control parameter, y label population show. Okay, and if you're running the program in your window in your text editor, okay, what happens? First we'll be asked the control parameter range, that is 1 to 4. Then you'll get the bifurcation diagram like this way. Okay, so I have discussed it already. 1 to 3 means we'll have only single value for attractor. Then beyond 3 it becomes 2, then it becomes 4, at certain point it becomes 8, then attractor becomes strange. For getting the attractors, we use the first loop, this loop, and getting all values. Once the attractor is reached, for getting all the values, we repeat the iteration again to make it sure you are getting the attractors and you're plotting the graph between attractors and the control parameter. So hope this is clear. Logistic mapping, you just go through the theory of what you have studied in your classical mechanics paper, non-linear dynamics portion. You just go through the theory and you just go through the program, and I have sent you a link through which you can do the programming in the using your phone itself. Try it out and try to work out this program in your phone, and all of you send the screenshot of the output that you have obtained. After doing this program in your phone, you just send me the screenshot of the output that you have obtained in your phone. Okay, so thank you. This is an work for you. You do it and send it to me. Okay, fine. And the next class we'll discuss Monte Carlo simulation of pi. Then we'll discuss radioactivity, simple harmonic oscillator, and one more thing is there, that is floating particle in a box, that is solving Schrodinger equation. Okay, with that this module will come to an end. Okay, fine.